Around 251.9 million years ago, Earth experienced the most devastating extinction in its history, known as the Permian-Triassic extinction event, or the Great Dying. This was not a sudden disaster, but a drawn-out unraveling of life across tens of thousands of years. At its peak, 81% of marine species and 70% of terrestrial vertebrates vanished. Entire branches of the tree of life were pruned away, leaving behind a silent world struggling to breathe. The extinction marked the boundary between the Paleozoic and Mesozoic eras, ending nearly 300 million years of complex life evolution. It stands as the greatest of the Big Five mass extinctions in the Phanerozoic eon. Unlike the sudden asteroid-driven demise of the dinosaurs, this catastrophe unfolded slowly, insidiously, a deep time unraveling driven by Earth's own internal forces. Scientists now pinpoint the main marine extinction pulse to a narrow window between 251.94, 1 plus or minus, 0.037, and 251.88, 0.031 million years ago, a duration of just 60,000 years, plus or minus 48,000. This precision comes from uranium-lead dating of zircon crystals in volcanic ash beds at Meishan, China, the official global stratotype section and point for the Permian-Triassic boundary. The boundary itself is marked by the first appearance of the conodont microfossil Hindeodus parvus, a tiny tooth-like fossil used globally to define the start of the Triassic period. Its emergence coincides with a massive disruption in Earth's carbon cycle, recorded as a sharp negative shift in carbonisotope ratios 20 cc, dropping by 4 to 7%. This signal, detectable worldwide, reveals a sudden injection of light carbon into the ocean atmosphere system. The leading cause of the Great Dying was the eruption of the Siberian Traps, a colossal flood basalt event in what is now northern Russia. Over hundreds of thousands of years, lava poured from fissures in the crust, covering millions of square kilometers. These eruptions were not explosive, but they were devastating, releasing vast quantities of sulfur dioxide and carbon dioxide into the atmosphere. The carbon dioxide release totaled between 3,900 and 12,000 gigatonnes, an amount so immense it raised atmospheric carbon dioxide from about 400 parts per million to as high as 2,500 parts per million. For context, pre-industrial levels were 280 parts per million, and today's concentration is around 426 parts per million. This surge triggered runaway global warming. As temperatures climbed by approximately 8 degrees Celsius, 14 degrees Fahrenheit, the oceans began to suffocate. Warm water holds less oxygen, and increased stratification prevented mixing between surface and deep waters. This led to Yoxenia, oxygen-starved, sulfurous oceans where hydrogen sulfide accumulated, turning vast stretches of the sea into toxic, lifeless zones. Marine life faced a triple threat: warming, acidification, and anoxia. As carbon dioxide dissolved into seawater, it formed carbonic acid, lowering pH and making it harder for organisms to build calcium carbonate skeletons. Reef builders like corals and calcareous sponges collapsed. The fossil record shows a dramatic loss of bioturbidors, organisms that churn sediments, evidenced by the disappearance of mixed sediment layers in marine rocks. The extinction hit hardest among marine invertebrates. Of 329 marine invertebrate genera identified in South China's final Permian zones, 286 disappeared. These losses were driven by elevated extinction rates, not reduced speciation. Organisms with calcium carbonate skeletons, especially those sensitive to carbon dioxide fluctuations, were most vulnerable. Endemic species, those restricted to small geographic regions, fared worse than cosmopolitan ones. Localized bivalves, for example, had no escape routes when conditions deteriorated. In contrast, widespread taxa had a better chance of finding refugia, areas less affected by warming or acidification, where they could survive and later recolonize. The Great Dying may not have been a single event, but a series of pulses. In the Meishan section of China, extinctions cluster around one major peak. But in other locations, like Lianfengya and Shaanxi, two distinct waves, MEH1 and MEH2, are recorded, each with different environmental triggers. This suggests regional variability in how the crisis unfolded. Some groups vanished earlier than others. Ostracods and brachiopods, for instance, went extinct up to 1.17 million years apart, far longer than the main extinction window. This decoupling of extinction timing complicates efforts to define a single event. Marine ecosystem collapse may have followed species loss by about 61,000 years, indicating a delayed breakdown of food webs. The Capetanian extinction, occurring 7 to 10 million years before the main event, adds further complexity. Also known as the Guadalupean extinction, it wiped out dinocephalians and large fusulinid foraminifera like Verbicinidae. Many fossils once attributed to the Permian-Triassic boundary are now redated to this earlier crisis, blurring the line between two catastrophes. Some researchers argue that the entire late Permian was a prolonged extinction episode, with two major pulses, 9.4 million years apart, separated by elevated background extinction. Under this view, the final pulse killed about 80% of marine species alive at that time, while earlier losses had already thinned biodiversity. This challenges the idea of a single great dying moment. Environmental stress wasn't confined to the final pulse. In the Bowen Basin of Queensland, paleoenvironmental analysis of Lapingian strata reveals repeated marine stress episodes in the middle to late Permian. These intermittent crises may have weakened ecosystems, making them more vulnerable to the final blow. On land, 70% of vertebrate species disappeared. The Karoo Basin in South Africa records a turnover from Dicynodon-dominated faunas to Lystrosaurus-dominated assemblages, a shift marking the extinction. Dating suggests this terrestrial collapse may have preceded the marine event by up to 370,000 years, though the timing remains debated. In East Greenland, however, terrestrial and marine extinctions appear synchronous. There, animal decline is concentrated over 10,000 to 60,000 years, with plants showing delayed responses, some taking hundreds of thousands of years to reflect the full impact. This suggests terrestrial ecosystems may have lagged behind marine ones in collapse. In the Sydney Basin, chemostratigraphic data support simultaneous biotic collapse on land and sea, but in Finnmark and Trondelag, Norway, terrestrial floral turnover occurred before the major negative -113 sea shift, indicating earlier land die-offs. In the Sunjiagu Formation of South China, terrestrial ecosystems collapsed before the marine crisis, adding weight to the idea of asynchronous extinctions. Plants were not spared. Spores from pollen-producing plants show deformities linked to increased ultraviolet radiation, likely due to ozone layer depletion. This could have been caused by volcanic halocarbons or an extraterrestrial impact. The Araguaia crater in Brazil, dated near the boundary, may have triggered seismic methane release and atmospheric damage. One controversial idea is the fungal spike, a sudden increase in Reduviaspironites, once thought to be fungal spores feeding on dead organic matter. This spike was proposed as a marker for the extinction in poorly dated rocks. But debate persists. Reduviaspironites may actually be algal remains, and the spike doesn't appear globally or always at the boundary. Newer chemical analyses of Reduviaspironites reveal biomarkers consistent with fungi, supporting a decay-related origin. Yet the pattern may reflect localized lake environments in the early Triassic rather than a global zone of death. The spike might instead signal a shift to stagnant freshwater ecosystems after marine collapse. Beyond direct volcanic emissions, secondary processes amplified the catastrophe. Magma intrusions into coal and oil deposits may have ignited them, releasing additional carbon dioxide. Methane clathrates, ice-like deposits of methane on the seafloor, could have destabilized due to warming, injecting vast amounts of potent greenhouse gas into the atmosphere. Novel methanogenic microbes, nourished by nutrients from volcanic ash, may have proliferated, producing more methane. This biological feedback loop could have accelerated warming. Meanwhile, intensified El Niño events disrupted global climate patterns, worsening droughts and marine productivity collapse. Ocean acidification devastated calcifying organisms. With carbon dioxide levels soaring, seawater pH dropped, dissolving carbonate structures. Organisms using hemocyanin or hemoglobin for oxygen transport, like many arthropods and vertebrates, survived better than those relying on hemerythrin or diffusion, which were less efficient under low oxygen conditions. Bioturbators, organisms like worms and crustaceans that mix sediments, vanished almost entirely. Their absence is recorded in the geologic record as a loss of the mixed layer replaced by laminated, undisturbed sediments. This indicates a collapse of seafloor ecosystems and nutrient cycling. Among survivors were articulate brachiopods with hinges, which slowly declined after the event, ceratite ammonites, which diversified in the Triassic, and crinoids sea lilies that nearly went extinct but later rebounded. These groups endured, perhaps due to broader environmental tolerances or access to refugia. The Great Dying was not the end of life, but a reset. Recovery took millions of years. The early Triassic world was dominated by disaster taxa like Lystrosaurus, a hardy herbivore that made up 95% of some fossil assemblages. Ecosystems were simplified, with low diversity and simple food webs. It took about 10 million years for marine biodiversity to approach pre-extinction levels. The recovery was slow because conditions remained harsh: high carbon dioxide, low oxygen, and unstable climates. Only when these stresses eased could complex ecosystems re-emerge, paving the way for the rise of dinosaurs in the later Mesozoic. The Great Dying reminds us that Earth's biosphere is fragile. It was not an asteroid, but Earth's own geologic machinery, volcanism, carbon cycle disruption, and climate feedbacks that caused the worst catastrophe in life's history. Today, as carbon dioxide levels rise again, the deep time record offers a warning. The consequences of rapid carbon release can last millions of years.